accepted as true, then doing the derivative of ln of x then becomes a little more straightforward. Because really, if you think about it, derivative of ln of x equals 1 over x, it doesn't make a lot of sense unless you know what the definition or what a definition of natural log is. And so the video kind of stopped there after number 1. So I thought what we could do is we could look at, 2 through 5. That's kind of a little block of questions that I feel like if you watch the video / remember pretty well, you got a great chance to be able to do 2 through 5. Just various forms. ln has various roles in that. So give those a shot. I'll be around to help if you need help getting started. As always, feel free to talk to each other, compare. Put number 2 in kind of the typical case. What you've got here is the derivative of natural log of some function. It's composite, obviously. I suppose we could consider it that since the input is not just an x. And so the derivative of ln, here's the way I usually put it is, the derivative of ln of something is 1 over that something times the derivative of that something, right? So you could use the letter u to think of it as a substitution, or you could look at it from this perspective and say it's 1 over 3x squared. So it's 1 over the input times the derivative of the input, so times 6x. Obviously, we can simplify this quite a bit. How about 2 over x for a clean simplification? Does that work for everybody? All right. So I feel like number 2 really follows kind of what the video talked about, and it's all kind of a nice, neat package. Number 3 is a little bit different because I'd say with number 2 and number 1, kind of the main function or the main thrust of the function was ln. I don't think that's the case here, right? If we think about differentiating this, what rule would we think of as the main rule for number 3? A power rule, right? So it's like a chain rule, but the big part of that would be the power rule. So for this one, I think we'd go 6 times natural log of x all raised to the 5th power times, here's the only spot where anything regarding ln really matters, the derivative of the inside, 1 over x. So again, if you wanted to simplify it and write it as 6 natural log of x to the 5th all over x. Fine. Don't have to do that necessarily unless you're matching up multiple choice. Guys all look pretty good, right? Yes? Okay. And then number 4, finally on this page, d dx of x to the 4th ln of x. Again, kind of like number 3, the main thing is not necessarily ln of x. The main thing here would be product rule. I threw this one in on you just because I know that this is always one of those things that's hard to see. I feel like you guys have probably gotten over that for the most part, but I think one more time, at least in this little section, not a bad thing to look at. So it's going to be 1d2 plus 2d1. So we'll put 1. The only time that ln really comes into play here is when you do d2, right? So 1 times d2, so x to the 4th times 1 over x plus 2 d1 4x cubed. We can simplify this to be x cubed plus 4x cubed natural log of x. Perhaps that would be a clean way of doing it. There's other things you could do as well, but that's probably pretty good. So do you guys have any questions on 2, 3, or 4? It's very mechanical, right? It's like if you know the skill, if you know the rule, you execute it. Shouldn't be too bad. Okay, fair enough. Let's take a look at the last one. Number 5 is right here. There we go. So kind of like before, we've got a mix of things, right? This is d dx of ln of x squared. So what's the big rule here, the overarching rule? I don't know. What do you think the answer? I'm just looking for your answer.
Chain rule?
So overall, it's a big chain rule. But when you think about the outside, we're talking about the derivative of ln, right? Yeah, this is a big old chain rule. In fact, couldn't you say that it's a function inside a function, and that whole thing is inside another function? It's like a double chain rule, sort of. So as we start off with what Caroline suggested, let's differentiate the outside. The outside function would be natural log. And so the derivative of natural log of the input is just 1 over the input, right? So it's going to be 1 over the input. But then because of the chain rule, we've got to consider the derivative of the input. So the derivative of the input, or I guess you could say the input is thing I'm putting in orange there, well, it's another ln, right? So the derivative of that would be 1 over x squared. Yep, 1 over the input. And then, as mentioned before, there's another tinier box. So you multiply by the derivative of that, and you do get 2x. Again, we could clean this up a hair. We could write it as something like 2 over x times natural log of x squared. I don't know, something like that. Because there's an ln there, we could do a lot of manipulation, but you just leave it at that point right there. Okay, any questions? All right, awesome. So we don't often talk about, or we don't often have a chance to talk about logarithmic differentiation, but I think we do. And so what I'm going to say about this is logarithmic differentiation is something that is not part of the AP curriculum framework. It's not anything that you would be tested on an AP test, but it is something that I would say, like, if you went on to take Calc 3 or something, they would assume that they would hope perhaps that you had heard of it or would be able to pick it up quite quickly. The calculus of this is not very hard. It's not any harder than what you've just been doing, and you all seem comfortable. So for you, it won't be too difficult. The hard part might be remembering all those log properties. Remember those? That's kind of the main issue here. So I thought I'd show this to you, just a reminder of those log properties and show you what you could do with this. I put some notes up here as to why you would do this. If you look at the example coming up, number 6, can you see that overall it's a quotient rule? It's a fraction, right? You could turn it into a product rule, I suppose, if you wanted to flip up. That would work. But whether you did a quotient rule or whether you flipped up and did a product rule, wouldn't it be fair to say that anytime you did D high or D low or D1 or D2, you'd have a chain rule, right? So when you get these combinations of things, fractions and chain rules and products and all those sorts of things, then perhaps that's when this logarithmic differentiation thing would be best used. So that's a matter of opinion. I thought I'd show it to you. You can make up your own mind. And this could be applied on an AP test, although it's not required at all. So let me show it to you. Here's what we would do with this particular one is, and this would be the first step on any of these situations, we would do the natural log of both sides, right? And we're allowed to do that. You've seen that before in pre-calc classes. So we'd say natural log of y is equal to natural log of x minus 2 squared over, I'm going to go ahead and write it as x squared plus 1 to the 1/2. Just did natural log of both sides, right? Totally allowed to do. So we're going to leave that left side alone. I'm going to write this as natural log of y. And then on the right side, I'm going to, I think the word you guys probably learned in pre-calc was expand using log properties. Is that the word? Expand or condense would be the other way. So expand on this one. So let's talk this over. If you are doing the log of a quotient, you can expand it using what operation? Subtraction, yes. So it would be natural log of x minus 2 quantity squared minus natural log of x squared plus 1 to the 1/2. And if you remember these rules, you actually could have done the final expansion maybe in conjunction with that step. There's one more expansion you could do. Yeah, bring the exponent down on both of those inputs. So natural log of y equals 2 natural log of x minus 2 minus 1/2 natural log of x squared plus, that's supposed to be a squared, there we go, plus 1. Okay, so what we've done here is we have basically boiled this down to the simplest logarithmic expression we can. And so what we can do now is differentiate. We're going to use, I thought I'd throw this in because this also uses implicit differentiation. Remember that? Okay, so with implicit differentiation, it does say y prime. We could think of that as maybe dy dx. So what I would do is I would do d dx of everything. Derivative with respect to x of the whole thing. So what's d dx of ln of y? 1 over y times dy dx. Yep. Using the chain rule there, because we're doing d dx of a y term. And then I'm hoping that the rest of these will go pretty smoothly. Like for example, the first one, the derivative of 2 ln of x minus 2 would just be 2 over x minus 2, yep. Oh, we put that in there. Minus, the other one will be a little more complicated. I'll put 1/2, and the derivative of ln of x squared plus 1 would be?
2x over x squared plus 1.
Sure, yeah, that works. Doing the chain rule right away makes a lot of sense. And so, quite quickly, once we got all that natural log stuff settled, quite quickly we come up with almost a derivative. Remember, the goal is to find dy dx. We haven't found it yet. I just need to do what? Multiply both sides by y, and I'll have dy dx. We could probably do ourselves a favor if we recognize that y equals that original expression. So when we multiply by y, why not just multiply by that? Does that make sense? Because if we don't do it that way, we'll just end up adding a step onto the end, which is fine. But I think what I would do is I would write dy dx equals y, which is x minus 2 squared over square root of x squared plus 1 times that whole thing we already figured out, which would be 2 over x minus 2. We could cancel those 2's. That would become minus x over x squared plus 1. Now that it's kind of a holy mess right there, and you could, of course, do a distributive property and all kinds of things, and you get some simplifying. I don't know that you would need to do that. This would simply be a way to do that question. And really, like I said at the start, is this easier than doing a pretty complicated quotient rule? Yeah, maybe. Maybe not, but at least it's another option of a skill you could use. And like I said, if that original got more and more complicated, then maybe it becomes a little more clear-cut that this would be easier than a quotient rule, right? Because you could use the logs to simplify it, and then you got to admit the derivative part, you did that quick. So this puts a little more emphasis on algebra, whereas the quotient rule maybe puts a little more emphasis on the calculus. So just a way of thinking about it, take it or leave it, do it or don't do it. I'm not going to test you on that specifically. I'm not going to say, I want to see you use logarithmic differentiation. But if you saw an opportunity, you thought, maybe I could, then do it. I don't think that they would be frequent. I don't think you're going to take some test and be like, I used it 5 times. And be like, probably shouldn't have done that. I don't think there were 5 opportunities to do that. But there could be one that pops up, and if that serves you well, then it serves you well. Okay? All right, so the last one here, 5.1, I thought we would talk about. We definitely want to talk about this one. Is this right here. It goes through this whole little explanation. It says, because ln is undefined for negative numbers, we'll often see expressions of the form ln of absolute value of u. Because really absolute value generates a piecewise function, really. We can differentiate ln of absolute value of u as if the absolute value notation is not even there. I thought I would prove that to you here in just a second. I can't remember if we proved this last year in AB, how you would handle this. Maybe we did talk about it. You did or didn't? No?
I don't think I remember.
Okay. So I just want to prove it to you, how this would work. And we're going to use this example right here, ln of the absolute value of cosine of x. So again, I want to be really clear about this, why we would even worry about this. You can't do ln of 0, but you also can't do ln of a negative number either, right? And so by putting those absolute values in there, it allows for that input to be negative. Let me show you. I'll show you a more basic graph. Like if you were to graph y equals natural log of x, natural log of x looks something like that, right? It's only defined for positive inputs for x. It's not defined for 0 or negatives, and so you'd only get the right half of the graph. If, however, I'm going to erase all this in a second. If you wrote y equals natural log of absolute value of x, you'd still get this right side, but then you'd also get this left side. It'd be symmetrical. And you still can't plug in 0 because you just simply can't do ln of 0. But you would then be allowed to have negative inputs as well. And as you might remember, this really comes into play with when we're trying to solve differential equations. If the initial condition causes a negative input for natural log, this gives us a way to deal with that. We haven't done the integral stuff yet. We will soon. But this absolute value, just basically, you can't say that it really doubles your domain because the domain is already from 0 to infinity. It just gives you like the left half of the graph to work with as well. So here's what we would do. I would say if we want to prove this, let's write it like this. Let's say f of x equals, we're going to piecewise this out, natural log of cosine of x if cosine of x is positive. Make sense? And f of x equals natural log of negative cosine of x if cosine of x is negative. So this is kind of your basic definition of absolute value. Absolute value should always like expand out into some kind of a piecewise function, assuming that the absolute values had some sort of an effect. You could always expand it out into a piecewise. Okay, so let's find our derivative then. So I would then say, we're looking for a derivative, f prime equals, okay, so natural log of cosine x. Let's think about what that derivative would be. Wouldn't it be 1 over cosine? Times what? Negative sine. Which equals, if we did a little trig identity work, negative sine over cosine is? Negative tangent. Okay, so this would be, this top part is if cosine of x is positive. Okay, let's do the other part. So the derivative of ln of negative cosine of x, well, this would be 1 over negative cosine of x. Come on, there we go. Times, what would be the derivative of the input? Sine of x, right? It'd be negative sine x. So times sine of x. And once again, when you do a little trig identity work, what do you get? Negative tangent. Huh. And that's if cosine of x is negative. So in other words, it really didn't matter if cosine of x was positive or negative. We got negative tangent of x both times. Right? So this is obviously kind of a specific example. You could also prove this in general if you want. The bottom line is this, like the little description up there is appropriate to say, all right, well, if you've got natural log of cosine of x and you're differentiating it, you can differentiate it as if the absolute values really weren't there. You can say, all right, derivative of ln of cosine of x is 1 over cosine times negative sine, which is negative tangent of x, just based on the way that the piecewise derivative works out every time. So you could either piecewise it out, like I did in the red and the blue, or you could simply realize that it doesn't matter, and you could just do 1 over the input times the derivative of the input, as if the absolute values just weren't even there. Is that an okay proof? Does that make sense? Any questions? Did we do that last year in AB? I can't remember. I feel like we did, but the years are all blah.
I don't think Mother's class did.
Okay.
I don't know.
Yeah.
I didn't make enough of an impact. I'm sorry. You were probably absent that day. That's probably what it was. Okay. Okay, so we'll leave that alone unless you have any questions. Okay, fair enough. Let's take a look at 5.2. 5.2, just I thought these went well together because 5.2 just takes 5.1 and reverses it, right? It just undoes the concept you looked at 5.1, so they're kind of inverses of each other. So in 5.2, we're going to look at integrals that lead to ln, because in 5.1, we looked at derivatives of ln. So we're just going to try to go backwards to get to these, and I think you'll find some of these to be pretty straightforward. So you watched the video, hopefully, and you learned the pattern of the integral of 1 over x, or probably better said, the integral of u prime over u should equal ln of the absolute value of u. There's that one example right there. So let's take a look at numbers 2. Just like, well, I don't know. Let's just do this first page for now. Let's make sure everybody's doing real good. Yeah, I think there's a natural break at number 4. So let's do 2, 3, 4, and then we'll look at the other ones here in a second. So in number 2, you look at the integral, you look at the integrand in there. It's obviously a fraction, and so we'll get into this as we finish out chapter 5 in the next couple of weeks. But whenever you're doing the integral of a fraction, the first thing I think you want to ask yourself, is this the natural log pattern? In other words, is the derivative of the denominator exactly the numerator? And in this case it is, isn't it? So since the derivative of the denominator is the numerator, this perfectly already fits the natural log pattern. So we could immediately jump to an answer. It's equal to natural log of absolute value of the denominator. And then don't forget plus c. That make sense? Okay. All right, and then you look at number 3. Once again, it's a fraction. And so you have to ask yourself that question. Is it ln? And what you're really asking is the derivative of the denominator of the numerator. And the answer to that is? Not quite, right? So you could look at this as a u substitution. I prefer to look at it as a Timmy messed up the pattern situation because what is the numerator missing? A factor of 2. So if I just multiply the top by a 2, I would get integral of 2x plus 2 over x squared plus 2x. And that would exactly fit the chain rule pattern, but I can't just multiply the top by 2 unless I balance it out by multiplying the outside by 1/2. Okay, so now this does perfectly fit the chain rule pattern for natural log, and so I would write as a final answer 1/2 natural log of the denominator plus c. You could do u substitution there, no problem. Up to you. All right, and then finally, number 4. It's a fraction. I think the first thing you should ask yourself, to me, what's easiest, is the denominator's derivative, the top. The answer is no. We're off by what factor? 3. So again, it's been messed up a little bit. Multiply the top by 3. Multiply the outside by 1/3. And now it does perfectly fit the natural log pattern. Everything's adjusted and balanced out from what I did. So I could write the answer as 1/3 natural log of the denominator plus c. Okay, so remembering well or doing well? Yeah? Okay, well, let's take a look at our last several questions in our section here. 5.2, number 5 and number 6. And then we'll do number 7 here in a little bit as well. So a question like number 5 is obviously a fraction, but when you ask yourself the question, is the derivative of the denominator at the top, the answer is a big no, right? A real big no, because you can't look at it and be like, oh, if we just multiply the top by 5 or 2 or something, then we're good. It's clearly something else is going on, right? So can I give you something to think about as far as what you do with this? Because when you think about these being out of context, right? You're taking some quiz or test, the AP test or a loop quiz or whatever, and you just see this is like number 11. The previous question had to do with related rates, and the one before that had to do with like the product rule. It's like totally out of context. You look at this, you're like, I have no idea what to do. So here's the general rule. If you're doing the integral and the integrand is a fraction, but the degree of the top is bigger than the degree of the bottom, probably what you need to do is division. Actually do the division that the fraction's telling you to do. And so number 5 is pretty straightforward. Basically divide every single term, top and bottom, by x. Just basically reduce it by a factor of x. And so this one would look like this. Integral of x plus 3 minus 7 over x dx. You see what I've done there? I just divided the x into each numerator term like it's asking me to. So x squared over x is x. 3x over x is 3, and 7 over x is just 7 over x. Once we've done that, of course we haven't done any anti-differentiating yet. Now we would do our antiderivatives. You see it made it really easy, right? Just go 3 terms. So you'd get 1/2 x squared plus 3x, and then how about the last term?
Minus 7 log natural log.
That's right. That's right. So that's why this is in this section, because natural logs will, in general, come out of these. So you'd end up something like that. So we kind of did the easier one together there. Number 6, though, is a little tougher. Can you see that once again, it is a fractional integrand, but the numerator has a higher degree than the denominator? So division is still indicated here, but you're dividing by a binomial instead of a monomial. So what are your two options?
Long division.
Long division or synthetic division. And so I want you to practice this, right? This is definitely a thing that you want to be good at. But what is the little trick? It's not too bad. There's a little trick kind of waiting for you on this particular question.
Find a zero.
Say again?
Could you just find a zero?
Find a zero. Not finding a zero.
I was thinking it was a trick.
Just so the nature of this question has a little bit of a trick you want to be careful of.
Well, it doesn't have an x squared factor.
Something's missing, right?
Yeah.
So in order to use synthetic division or long division for that matter, you've got to have descending order of degree. You need to have each degree value or each degree place filled. And so you're missing the x squared like he said. So we need to input like a 0x squared in there when you're actually doing your division. So I'll leave it up to you. I'll give you a few minutes to do that division. And then we'll check it out, see how you all did. Get a quick survey from you. How many of you did synthetic division with this? Synthetic? Blake, Lenny, did you guys do synthetic also?
Yes.
So everybody did synthetic. I think it's a wise choice. I like it. Okay, so we do the synthetic division off to the side. So a synthetic division, we would go -2 in the little box. And it would be 1x cubed, 0x squared, -4x, and 7. You leave a little bit of space. You bring down the 1, and this is where we start the little process. We multiply the divisor times the 1. We write the result right there. And what do we do with the 0 and the -2? We add them up. So -2 as a result goes there. Then I multiply these two together. When I do that, -2 times -2 is 4. I add those up and I get 0. Interesting. Then I multiply these two together, and I get, of course, 0. Add those up and I get 7. Okay. So what I do then is like reconstitute the polynomial over here. We'd say antiderivative of 1x squared now, right? Because we reduced the degree by 1, and so we're down to x squared minus 2x. There is no constant term here, so the 0 is, so I'm not going to write that. And then I'll put plus 7 over the divisor dx. Look good? All right, so then I think, again, once you do that, you'll find the calculus to be pretty quick. So it'd be 1/3 x cubed minus x squared plus 7, natural log, absolute value of x plus 2 plus c should be your answer. You guys have any questions? So I think the key for you is going to be quick recognition of this, because again, I'm thinking out of context, final exam, AP test, whatever. You might not recognize this right away, so my hint to you is if you've got a fraction and the degree of the top is higher than the degree of the bottom, then you're pretty much going to always be doing some kind of division, whether it's the really easy division like number 5 or the somewhat harder synthetic division number 6. I think you're going to get division when you have that scenario. That makes sense? I tell you that just for a quick identification, so you don't sit there and spend 5 minutes being like, is it ln? I don't know. Is it arctangent? I don't think so. You could just jump right to it and say, hey, degree, I'm going to divide. And move to it fairly quickly. Okay, so the final example in 5.2, I think, is right here. Yes. So finding area. So this says find the area of the region bounded by the graph of that equation, the x-axis, on the interval 1 to 2. I don't know, perhaps it'd be useful to graph this on a calculator just to get a sense of what the region looks like. Feel free to do that if you would like. We're looking for area. So give it a shot. If you graph this, there's no zeros, so this would have to graph like this, wouldn't it? Go. Is that about right? About right? Because you got this guy right here. Okay. Anyway, we are really not concerned about the whole graph. We are mostly concerned about the interval 1 to 2. So, I don't know exactly, let's see here. So, I don't know, say 1 to 2 right there. We're looking at that area. It's maybe important to know that this is always above the x-axis. I mean, it didn't really give us room for interpretation, but that's how it is. So, that is helpful. So, we're looking for this area right here. And did you guys all do like Riemann sums and do your limits and stuff? What'd you guys use? Definite integral, right? It never said you had to use an integral. It never did it? Sorry. You could do that though, couldn't you? I mean, it would be probably unpleasant, but we'll do definite integrals, right? Yeah. I didn't intend to scare you. No, you don't. Yeah, so, for quizzing and testing purposes, and really the AP test, it's really about matching. It's about matching a Riemann sum to a definite integral or the other way around. Really, that's all it's going to be about. I just can't imagine they'd spend a whole FRQ watching you do all this algebra and also memorizing those little formulas, right? So I don't think they do. Okay, so we would say integral from 1 to 2 of x squared plus 1, over x dx. That would be the definite integral you'd want to set up to find that area. And do you guys recognize that it's just the division, right? We just reduce everything by x. So you'd get integral from 1 to 2 of x plus 1 over x. Yes? Do your antiderivative. You get 1/2 x squared plus natural log of x. Evaluator from 1 to 2. We then do FTC 1. And let's see, when you plug in a 2, you're going to get 2 plus natural log of 2. Minus, when you plug in a 1, you're going to get 1/2 plus natural log of 1. And of course, natural log of 1, like we said before, we were talking about, is 0. So you could simplify this a little bit. You could go 2 minus 1/2 is 3/2 plus natural log of 2. And stop right there. But you don't have to, as we talked about. So there we go. Do you guys have any questions on any of that stuff? Okay, so for tomorrow, I think we've got a video or two coming up. We've got some inverse functions and other exponential functions, and we'll just be ready to kind of go through that stuff. But as we kind of get ourselves ready for Thursday, we'll definitely give you an opportunity tomorrow and Wednesday for that matter. If any questions have come up for you as you're thinking about preparing for that test on Thursday, I'll give you that chance. So do ask, and I'll be happy to help you out. Okay? I think that's it. Oh, you're getting out like 10 seconds early. See ya. Have a good day.